is N. Emil J. Bjerrum-Bohr, and he will be talking about studying gravitational interactions and binary black hole mergers with on-shell amplitude methods. Professor Bohr, please go ahead.
Thank you so much for this opportunity to speak. So I will try to tell you about some recent progress we've made using amplitudes or merging methods from amplitude physics and GR problems. So we all know about the exciting development of measurement of gravitational waves, and it poses some interesting problems for theoreticians. And in the field of amplitude physics, people have been very focused on providing new theoretical insights. So first of all, there's very valuable insight in studying extreme gravitational interactions that we have access to through the gravitational wave from black hole mergers. And it puts pressure on us theorists to match the precision of the observations. And that has motivated a lot of interest in refined computational methods. So gravity has a long computational history in the field of quantum field theory, but in this sort of more modern takes where we use a lot of on-shell methods in amplitudes, there's been interest to somehow use some of these techniques developed for the Large Hadron Collider and QCD, but recycle them into gravitational computational methods. So I'll try to explain some of the stuff that we've been doing recently on such lines. So first of all, the theory of gravity is very much based on Einstein's theory. And Einstein's theory is very beautiful. It solves a lot of interesting problems and explains the gravitational interactions. But we have some mysterious places in its or there's some holes in our understanding, like for instance, what happens when we have very extreme gravitational fields, for instance, in the vicinity or inside black holes. We also famously don't know a good way to extend Einstein's theory to quantum mechanics. I'll explain how we are working with it in terms of quantum field theory. We also investigate these questions of how to formulate gravity bests. Like in the amplitude methods, it's very convenient to start with a flat space formulation at infinity, but there's definitely some value using curved space formulation also in the QFT. And if we are to extend Einstein's theory into quantum theory and doing a minimal extension, there's a need to consider additional terms to Einstein's theory. So there will be some bounds and extensions through higher derivatives in the theory. And it could also lead to interesting questions such as what is the graviton, what is its properties, what is its mass? There's various theories there. And finally, gravity is linked to the universe's evolution. So there's some big questions out there to focus on. So the main thing we'll look at today is to provide, I would say, a good theoretical foundation for working with GR in terms of quantum field theory, and see how far we can take that, and also what kind of answers we can answer using this approach. So the traditional quantization of gravity started in 1960s. It in fact started a little bit before with the work of Guptas and others, but the sort of standard particle physics version of general relativity, where the Einstein-Hilbert-Lagrangian was a starting point for the derivation, started with work by Feynman and de Wit, and their approach were very simple. They basically just took the Einstein-Hilbert-Lagrangian and they expanded the fields, the metric field, and there's various ways you can do this, but you can do it around flat space definitely, and see any quantum extension to that as this kappa h bar. And now you can easily, instead of using equations of motion, reformulate this theory in terms of a path integral. That means you get an interaction, and you can derive vertices as in a particle theory, and you can basically compute physical scattering amplitudes using Feynman diagrams. And this has been used in the general relativity community for a long time. And there's a famous paper by Kovacs and Thorne from 1977 that definitely uses these kind of approaches. But one thing that has changed since then is that if we look back, the off-shell QFT methods, I mean, using really Feynman diagrams and putting things together was the standard. But today we have also learned that we can use a lot of new techniques like unitarity and other methods to simplify things and especially keep things on shell and thereby provide computational efficiency. So how can we talk about quantum gravity? So a good way to do this without having to think about too much about a fundamental theory is to basically take the viewpoint of Weinberg to view the quantization of general relativity from the viewpoint of effective field theory. So we cannot just use Einstein-Hilbert alone because we know it leads to infinities and it leads to, in particular, ultraviolet divergences in the theory. But we can include higher derivative operators everywhere in the formulation and thereby provide a framework that allows us to work with gravity as a field theory. So the way we do that is to take the Einstein-Hilbert term, which is the first here, and the matter, and we basically include all the type of interactions that we could have in the theory, also involving high derivatives. That provides order by order in energy expansion of the theory, and we know this from things like particle physics as an effective field theory. So basically this description is an effective field theory and it's valid at low energies. And we can answer all sorts of particle physics questions using this model. And we of course have an expansion both in the gravitons but also in the matter fields. The advantage of using this framework is basically just to have a consistent starting point, but it's also a very natural generalization. I mean, in fact, if you look back at how Einstein derived his field equations, there's nothing there that somehow dictates that you could not include higher derivative terms. It's just clear from the way it's formulated that these things will be very minimal give very minimal effect to the equation of motion. So it poses actually a quite ideal setup for a QFT analysis of black hole mergers. And it also has some interesting aspects. If you are concerned about fundamental theories, you could work out more fundamental physics and you could derive some consequences that you could compare to this effective setup. So using this effective field theory approach, you have a direct connection between this kind of phenomenology you would like to do from, for instance, gravitational wave mergers or multi-messenger astrophysics, but also to, say, string and supergravity theory extensions, because these theories will be easy to embed in an effective framework and provide some bounds on coefficients in this. So the recent key research direction in the amplitude field is to test general relativity, to do precision tests using QFT methods. And the reason this is interesting is that if we do this, we have methods that are actually more precise in certain analytical regions than the current state of the art using numerical methods. So it's a very nice complementation of what we're doing in GR already, testing things. But now we can get more precise in those regions, especially the large in-spiral regions where we have the two black holes quite far away, and we want to understand almost periodic motion. And an interesting fact is, and this is also something that Thorne saw in his paper by Kovacs, is that actually it can be more efficient to directly do QFT than solving Einstein's field equations. And the reason for that is maybe that the world is in fact quantum mechanical, and the way that the path integral works and the way it somehow deduces the classical physics is very organized in a nice way. So we will explore this in our computations. So the goal of the sort of immediate goal is to identify from QFT a precise and efficient extraction of classical physics from amplitudes, and we can bank on the fact that it provides us a potential to discover new physics, because if we can do this and we can provide the precision, we have a better background for detecting new physics. And if we can analyze gravitational wave events faster and more accurate, we can provide a better analysis and thereby an easier way to test GR. So to go into the matter of what we do in the computations, so the problem in QFT, in a scattering theory, to relate a scattering loop amplitude to an interaction potential is somehow at the heart at our difficulties. So one thing is we have to provide amplitudes to some given order, and then we have to choose a way to derive gravitational interactions. That means we have to spend some time understanding how GR and amplitudes or the scattering amplitudes from the QFT is related. In PN, we have a quite well-defined framework for doing this, and we will see how we can generalize this to the relativistic case. And of course, we have to make some assumptions in all this. So we restrict to quite classical objects, point particles, and we make them scatter at very classical distance scales, meaning that we are quite far away from the horizon of a black hole. So this basic problem we start with is to provide a Hamiltonian for the scattering of two massive scalars. And from the literature, we can go back and find the Salpeter equation that links the Hamiltonian to what we call the scattering potential V. And we have the kinematic terms. In the non-relativistic limit, we can actually quite easily see that the potential, the interaction potential, and the amplitude is provided through a Fourier transform in flat space. So when we have the amplitude and we take the amplitude, the space part of the amplitude, we can do a 3D Fourier transform between variables Q and R and go to an R space definition of a potential. And if we want to extend this also in a relativistic scheme, also if we're doing it in post-Newtonian physics, we have certain iterations to consider. So the equations that relate the scattering amplitude and the potential are linked through a iteration formula, where we basically, to leading approximation, use the Fourier transform to go between amplitude and potential. But at next order, we have to consider the energy propagation of the iteration of the potential, and that is this integral equation we have in the end, and it will we can work this out order by order and determine the potential, but we have to do that in a clever way in order to generate things efficiently. So I'll come back to this point. Then, in order to work with classical gravity from a quantum theory, it's most logical to limit our Feynman diagrams in certain ways, meaning that we only consider the diagrams that are that doesn't, for instance, involve annihilation channels like anti-black holes. We don't have backtracking diagrams, and we don't have antiparticles in this. So it's not the full Feynman set of diagrams. It's a certain restricted part that we can easily link to the classical physics. So in the case of scalarless gravity from a quantum theory. We start with the Einstein-Hilbert-Lagrangian. We don't actually to the leading orders have to consider the effective terms. They will appear later when we increase the orders of loops. But to leading order, we can just start with the Einstein-Hilbert term. So in this term, if we work with spinless fields, we can write a energy stress tensor down at T mu nu for the spinless field. And for a scalar, it looks of the form written down here. And we contract now with the metric G mu nu, and we have the Einstein-Hilbert term. So in order to work with this in the context of Feynman and de Wit, we would have to expand the curvature tensor, the scalar curvature tensor, and the stress energy element, and derive vertex rules that is order by order in this perturbation field, and also the scalar field degrees of freedom. The processes we will derive our physics from are 2-to-2 scattering processes in the path integral. So it's basically scalar scattering, where the only thing that happens is that we have an exchange between scalar particles of energy and momentum. So from side in to out, there's some change of these p variables here, and that's where we can derive our observable. And of course, this is a very plastic way of working with DR. We can do many other possibilities for fields, so we can work out examples of many other objects in the gravitational space that could interact. But to leading order, spinless fields is the most interesting problem. So then the first task is to work out the amplitude to all loop orders. So why is that? What happens is that if you work out the tree-level interaction, it's relatively easy from the Feynman rules to verify that you get a term which is 1 over q squared times a coefficient. And if you keep things relativistic, you have here a relativistic factor gamma. If you Fourier transform this to go to the potential, you see immediately that this will lead to a 1 over r potential, which has the numerator factor, which is g m1 m2, exactly as you expect from Newton's law. But you also see that this is not what we expect from the theory of general relativity, because it doesn't give all the post-Newtonian effects that we expect. So a surprise actually in gravity treatments in QFT is that a lot of the classical correction effects comes from loop diagrams. So we can start writing down the tree diagram, and we can start working a 1-loop diagram, 2-loop diagram, and there's various forms as we go up in loop. And then we can do all this in a center of mass energy scale. But if we look at the most general diagram, what we have to do is, in order to see where we have classical physics, we have to reintroduce Planck's constant everywhere. So normally when we do field theories, we are considering units where we put h bar and speed of light and other constants to 1. But in this case, we have to actually go back, and we have to take the massless degrees of freedom, and we have to rescale, put in the h bar factor as a non-trivial factor, and see the scaling behavior. And then we have to take the loop amplitude that we have derived, and we have to Lorentz expand around h bar. So in general, at L point or L loop order, that will lead to a Lorentz expansion that starts with a L+1 h bar term here. And it has some Q dependence, also depending on the loop order. So what we have to determine is the numerator factor, which depends on the specific in the loop diagram. So from that point of view, we can see where we have classical physics in the problem, and we can use this classical physics to derive consequences for observables. So it's a little different from the way we are normally doing QFT, because we have to make these considerations quite early on in the computations. In the context of amplitudes, it's very customary to work in what we know as the post-Minkowskian framework. So the post-Minkowskian expansion of Einstein's theory of relativity is a way to think about the problem that has received much attention in this amplitude community. We can basically think of this as a resummation of a post-Newtonian expansion. So the post-Newtonian expansion will have an expansion in velocities and Einstein's or Newton's constant. But in the post-Minkowskian expansion, we have basically resummed all the velocity contributions and kept everything relativistically invariant. So we don't have to work out more diagrams if we are just keeping everything invariant in corresponding to relativity. And that provides a very nice link, because if we're working with these scattering amplitudes that are directly 4D scattering amplitudes, it's very simple to utilize for the computation the modern amplitude computational framework, and then link that to post-Minkowskian observables. And pushing this way of working with gravity was very much pioneered by Thibaut Damour. So in the way of thinking about amplitudes in a post-Minkowskian framework, we now have to think about how do we construct loop integrals. So we have various techniques at hand. We have on-shell integrand constructions, and I will give some more details of that. We have to face things that we also face in normal particle physics, like multi-loop integrations using IBP relation reduction. There's various computer programs that can help with that. And we are also using very much modern integration techniques, integration by region, various numerical packages that can keep track of contributions from the various loop integral, and also provide numerical answers to check with analytical approaches. And we use a lot the PD approaches and this way of setting up these computations efficiently. So important point to use unitarity, we need to know what we can capture from this. And it turns out that it's very nice that the long range behavior of these interactions are exactly what we can easily capture by the unitarity cuts. So the unitarity cuts have some, if we are doing QCD, some areas where it's harder to use them. We have to use more advanced methods for unitarity cut. But here in the long range behavior that we're interested in gravity, we can use the standard approach, and therefore it simplifies computation. So the unitarity approach is basically it's the statement that the S matrix is unitary. So we start from an amplitude here, which we can look at the imaginary part of, and we can link it to the real part of that amplitude. And by consistency, we can tell a lot about the one loop amplitude from these considerations. So I will explain a bit better, but the main way we use this is to, for instance, if you want to compute a given loop amplitude, to compute some tree amplitudes which don't have loops, and to make a cut of, say here, graviton lines, and to use the fact that when we do the cut, we can put all these lines on shell, but the loop integral that is left, even when it's cut, still tells us a lot about the full amplitude, and we can use that to produce results. So this was pioneered in various papers. There's an early paper by Neil and Rothstein, but also a paper by myself and Donahue and Van Hove, where we pioneered the one loop computation of this in a modern context. Then we can use some tricks which comes from work that has been done in Yang-Mills theory. Basically, that if we consider string theory, we can see that Yang-Mills theory and gravity are related through a square. Basically, the 3-point amplitude squares always to gravity amplitudes. So instead of working out gravity amplitudes using Einstein-Hilbert-Lagrangian, we can actually start from Yang-Mills expressions and these KLT relations that link to gravity. And this is very nice if we embed it in some modern techniques, among other things, algebraic methods that rely on some string theory structure of amplitude. So I will explain also how that comes about. But first, before we start, it's good to do the one loop example. So at one loop, if we want to compute the effects of gravity at one loop, we are considering a cut with 2 trees and 2 graviton lines. So the 2 tree amplitudes we can put together from the various methods we have available, and then we do the cut. And we see, if we consider the various integral functions we have in the amplitude, that we have something called box functions with 4 propagators. We have triangle functions with 1 propagator, say on the left side, 1 propagator on the right side, and also some function, say, without any propagators on the massive line. So, and then we have additional contributions, but we don't have to consider those contributions if we're just concerned with classical gravity. So for classical gravity, this is enough to constrain the one loop amplitude and derive this Lorentz expansion that I showed before. So what we have to do is we have found the scalar integral basis. Now, in front of each of these integral functions, we have to derive coefficients. So we can write out what we expect from the Lorentz expansion. So, for instance, if we look at the general formula, we should expect a term that comes with minus 2 powers of h bar, 1 power of h bar, and h bar to the 0. And then we can analyze the various integrals that appear. So for instance, the box function is the only one that will contribute to the maximal power of h bar inverse. While if you go to the next order, it will be mixed in with effects from the triangles. And if we go to the 0 order, we get a mix of the box, the triangles, and also the bubble term here. Now, before people worked on all this, they observed some interesting empirical observations, which is that the classical parts, the part that matters for GR, is somehow understood by certain diagrams. So for instance, in this case, we should expect the triangle diagrams to give the main contribution, and that this coefficient here to provide the important contribution to the observables. So what we have to understand here is how these box coefficients play a role in the amplitude and how they, for instance, disappear from the potential, the gravitational potential. So we can write out the various integrals. We see that the boxes have 4 propagators and 2 of them are massive. The boxes comes in 2 variants. There's the one that cross the graviton propagators, and there's the one that where the propagators are going straight across. Then we have the triangles that has 2 massless propagators and 1 massive propagator on each side of the 2 diagrams. So if we keep only the classical pieces, we can expand out what the integrals give us. So the classical integral from the box will give us something q squared. The triangle integral will give us something q to the first power. And we can also work out the coefficients here in D, in fact, where we have kept D arbitrary. So we have not even imposed 4-dimensional physics. And now something interesting happened. So I showed you before that in order to compute the potential, we have to solve the iterative equation. And we can derive the iteration in this case. And we see in the iteration, we generate something that is conspiring with the term we get from the boxes. So we see here that when we compute the box, we generate some terms which are q squared, and this term is exactly the term that enters in the iteration. So the q terms cancel the iteration q term, and that means that the potential in this case that we can derive, which is the sum of the amplitude and the iterated contribution in order to go between amplitude and potential, is in fact what we get from the triangles alone, plus some piece that depends on the type of coordinates we have picked. So if we pick coordinates in the right way, we can basically get everything physically from the triangle coefficients. And this follows from the Lippmann-Swinger subtraction if we are doing this in the correct way. And if we look at other approaches like the one by Byrne et al., which using effective field theory matching, it's the same result, just a slightly different logic. But the effect is that we have to make sure that these singular terms that appear from iterations, they disappear when we are considering something like an interaction. Now, after we have the potential, we can see that the classical part of the amplitude is this piece here, and a quantum correction. So the lesson we learn from all this is that it's only part of the amplitude that is relevant for deriving observables in general relativity. And we have to make sure that we understand the scheme, how we are matching quantum mechanics and the corresponding results in classical gravity. So in order to go on to higher loop orders, we have to repeat what we did at one loop, but we also have to generalize how we are doing these subtractions so we are sure that we do them correct. So at two loop, we can set up a similar approach. We are starting now with a multi-loop cut, and we are using again a representation in terms of scalar integrals to generate the full non-analytic contributions to the amplitude. That means everything classical and superclassical. But now we have to consider a more complicated cut because we will in principle have three graviton lines across from the two trees. So in the three cut case, we see that we have two trees that has three graviton lines that we cut, and the cut mathematically now is this contribution of two 5.3s with three loop momentum lines. We have to consider all the permutations, so all the crossings of the various gravitons in the cut, and there's a symmetry factor as well. And then we have to carry out the integration of L1, L2, and L3 in order to have the cut expression. Then for the cut, we have to see what type of integral functions we have in play. So we expand out the amplitude in terms of an integral basis. That basis will now be a bigger basis because it involves now double box functions, mixtures of box and triangle functions, double triangles, and so forth. And we can use unitarity to fix the coefficients in front of the master integral. So the full amplitude that we want to find at two loop is the combination of the three cut contribution and the self-energy contribution. So the self-energy contribution is new at two loop order. And the three cut can be deduced from the three particle cut. So here in the self-force contribution, we get a self-energy amplitude, which is the sum of various diagrams that involve the one loop, but with some graviton emission on the same side of source. So it's like a correction to the source one loop amplitude. And these pieces are important because if we are not accounting for them correctly, as we will see, we'll get we'll get infrared singularities that are that has to be cancelled. So in order to derive the three-particle cut, we then have to consider the types of diagrams like below. So these are the integral functions that we will see, and we have to find the coefficients of each one of these pieces from the cut. So in order to work out the master integrals, we are using some computer programs like this program called Light-Red or Fire or Kira. Now I want to make a little detour because at the one loop order it's relatively easy to work with the trees, but as we go up in the complexity of the cut, we need to be more efficient in the way we represent the amplitude. And here it turns out that string theory is a very good helper for making a superior understanding. So if we work with Feynman diagrams alone, Feynman diagrams sum separate kinematic poles. So we have a sum over terms that comes with different kinematic poles. And when we sum these things, we get the full amplitude. In string theory, on the other hand, we often get a compact expression that automatically has all the poles, but don't come in separate kinematic contributions. And an example of where we see this structure quite clearly is in these approaches that are close to string theory, like CHY, where we can generate Yang-Mills amplitudes in a sort of very string-like manner. So we are here using the scattering equations and this auxiliary language to rewrite amplitudes in terms of contours. And what we get from this formalism is these numerator factors that we see here with the n minus 2, and we have fixed leg 1 and n in the end. So the advantage of this is that we can keep leg 1 and leg n here as the scalar integrals, the black holes, and all the legs here in the middle as in Yang-Mills theory gluons, but we will see how we can square that to gravitons. But the clever thing is that in this formalism, 1 and n, the endpoints are fixed because the amplitudes are or numerators are so-called numerators that have fixed the endpoints. So we don't have to consider poles where 1 mixes in with the beta set here. So all the beta variables in the set are all the massless degrees of freedom. And now we can generate gravity amplitudes in a very neat way. So on one side, we start with the Yang-Mills theory. If we were doing normal Yang-Mills color amplitude, we take these partial amplitudes on the Yang-Mills side and multiply by a color factor to get the colored Yang-Mills amplitude. But the KLC relations tell us that we can take the gravity amplitude and write it as these numerator factors times the same Yang-Mills amplitudes we would use to generate the colored Yang-Mills. So that means that the numerators, since they don't have poles, times the amplitude, gives us a very neat way to generate the gravity amplitudes. And all poles in this are simple because the gravity poles we have in the tree on the gravity side are linked exactly to the Yang-Mills side, meaning every pole we have is physical and there's no spurious poles. And then we can work out order by order numerator expressions for the various pieces at 3-point order. Yang-Mills squared is basically gravity. At 4-point order, gravity is the product of Yang-Mills times numerator, and we sum over all permutations. We can write this out in this form below, where we see the numerators square, but where the poles are given by the Yang-Mills amplitude. So we can use this to straightforwardly add any number of graviton legs we want in the cut, and we don't have to consider double poles. And as a further side, a recent result that I was involved in deriving is also considering more exotic particles than just massive spinless particles. One can also consider spinning particle amplitudes where the massive line is now what we would understand as a massive object that has a spin and a classical ring radius that is interacting with gravitons. And we derive this using a bootstrap. So everything is kept covariant and can be used as input in such computation. And there's a very nice match of this result with the result of what has been going on in the Uppsala group. So there's some interesting amplitude directions in this to work out fundamental physics for amplitudes using these objects that are very symmetric and covariant. So let's get back to the tree-cut. In the two-loop case, we work everything out. We find that the tree-cut contribution is this horrible expression where the sigmas now denote the various relativistic factors in the problem. But we see that when we have worked out that three-particle cut, there's an imaginary contribution. So in fact, this is where it becomes important that we have this analysis of the amplitude in play. So first we take the amplitude and we expand it out in powers of the h bar to derive the Lorentz expansion. And we see that if we also work out the self-energy, the imaginary contribution is cancelled by the radiative contribution. This was found by the group of De Vecchia, Heisenberg, Russo, and Veneziano. So that means that we have a consistent way to think about this amplitude, that in fact there is an imaginary part, but it is supposed to be there because it's a radiation piece that has to be cancelled. Now, as something magical happens, because now we will start to make contact with GR from the amplitude. So when we take the amplitude and we now go back from the Q expansion, that is the natural when we are computing the amplitude from the loop integral, to amplitudes rewritten in terms of the impact parameter space B, then we have to do a Fourier transform from Q space to B space. And now we start seeing the iterative pattern of the amplitude. So we see that when we are working out the Fourier transform to B space, the various amplitude components starts factorizing in very neat forms. For instance, at the leading order in inverse h bar, we get a very nice cubic piece that is the piece from first order in h bar inverse cubed. And that piece is linked to the piece we have in the h bar cubed factor here. So we see that there's a lot of iterative structure in this when we transform to B space. And in fact, this can be put into use into reconstructing the gravity iconal in B space. So if you write the amplitude as a 1 plus the transition element, we get this exponentiated formula like the follows, where we have the various phase shift delta L for the various loop orders organized in an exponential expansion, and the exponential will exactly make sure that the iterations are accounted for. And we see that to leading order, it's reminiscent of the tree amplitude we computed. To the loop order, first loop order, we get something reminiscent to the triangle contribution. And at two loop order, if we work it out, we get a slightly more complicated expansion. Now, if we take and transform the amplitude from B space to angular momentum expansion, we have to rewrite from B to J. Then we can also derive the scattering angle elements in J expansion, and we can see that we exactly reproduce the expected scattering angle of the gravitational binary problem to 1 p.m. order, 2 p.m. order, and also to the 3 p.m. order once we account for the radiation piece that we saw had to be included. So what is nice to see is that there is a way to make the amplitude physics connect with the general relativity, and that also considerations like cancellations of infrared divergences is, if we're doing them correctly, it demonstrates exactly the consistency of what we are doing. So I know that time is running fast, and I'll hurry up. At some recent results, I just want to give you a taste of what is interesting to focus on next. So we saw in the computations that we can do things brute force, but we gain a lot of insights from doing some basic observations of simplifying computations. And one such thing is that we can organize the integrand in a simpler way. And in that simplification, we can use a concept called the velocity cuts. So basically, when we put together the type of propagators we have in play, when we are looking at the cut expressions, we see that the mixture of crossed and non-crossed propagators, they will give us contributions as demonstrated here, where terms, propagator contributions are subtracted from other propagator contributions, but with varying I epsilon prescription. And this allows us to express the middle term here with the 4 propagators as delta functions, differences of delta functions multiplied together. And this follows from this basic identity that if we have a pole x and we are I epsilon above, and we subtract the pole with the minus I epsilon part, it is basically what we understand as a delta function on the real line. So we can use this prescription to rewrite the integrals from propagators to delta functions. And there's a lot of interesting physics in this. And we can see that it also organizes the computations we have to do, that the various contributions we have in play when we are looking at the cut, they come with varying delta function contributions. And we can organize the computation accordingly so that we focus on the pieces that provides us with the physics. So an example at one loop, it's the box and the cross box will give us these propagators. And if we write out what they give, we see that they will give us a piece plus a higher order piece in Q. And this piece will be cancelled in the subtractions. So in fact, when we are considering the various contributions to the computation, we can see that things are cut in such a way that they split up. For instance, if we have 2 propagators and we have the velocity cuts in play, it's like we have a 3 times 1 loop contribution. And we can also identify pieces that are connected pieces and thereby related to the pieces that very much play a role in linking to observables. So triangle contributions here at 2 loop will be linked to these nested tree structures. And that is very alike to the way that things are sort of in the world line formulation. So there's a direct link between the approaches using just normal QFT and also these approaches that are using the world line formulation from the start. And it, among other things, allows a very simple classification of things we have to subtract and the direct classical contributions that we need in order to get the correct observables. So this can be put in a more general context by considering an exponentiation of the radial action. So one can figure out that for the classical physics, there's a certain identity in play between what we get from the classical scattering element and also the radial action for this exponential formula. And what it gives, among other things, is a link between n, which is radial action terms, and the transition elements in the amplitude with these contributions here that are linked to iteration pieces. We can also use this technology to simplify the input trees that we want to consider, and thereby simplify how we generate the integrand that we are computing. So, for instance, we can start with the tree that involves the Feynman propagators, but rewrite it in such a way that we expose the delta function between the two 3-point amplitude and the piece that basically have no delta function. And for the general tree, we can generate some expansion that has a coefficient times L number of delta functions and so forth, all the way down to a piece with no delta functions. So this gives us a velocity cut tree diagram expansion that is very easily linked to the soft expansion of the tree amplitudes. So this helps how to construct integral topologies. For instance, we can see that the probe topology will be of the type that has no propagator and has all the propagators on one side, while the next to probe topology is one that has one propagator or delta function on one side and the rest on the other side. So this is a simpler way to generate the integrand than to do the whole thing, the whole cut, because we can eliminate certain pieces from the start. And this is also very linked to other approaches like the Queen Mary group, Brandhuber, Chen, Travaglini, and Venn, who developed a heavy quark way of thinking about this. And it is definitely linked, the heavy mass, to the small q expansion. So there's some interesting stuff to investigate which methods are the most simple. But just as a prelude, so using this framework, it's actually quite simple to now extend to higher loop orders. One can simply write out the various diagram topologies associated with the various cuts that we have in play here. And we see that each cut corresponds to a certain tree type graph. So we have to leading order the probe topology, which is a source linked to 4 other sources. But we also have other contributions like these line structures in the second diagram, or in this third diagram, we have 2 lines that intersect and so forth. And in fact, if we count a for loop, there's only 5 integral topologies that have to be considered if we eliminate a lot of the redundancy in the cut construction. So then one has to still work out the scalar integrals. In this case, there's about 40 integrals that can all be put into a formula with coefficients times integral function that gives us the amplitude. And from the various topology tree-like structures, we can then work out coefficients for the various contributions and see how that matches with the results which are currently in the literature. So just to conclude, so I hope I've given you a taste for how amplitude techniques can be surprisingly efficient in computing post-Minkowskian gravity computation and also bridging the gap to the current scene of observational data. It's important to acknowledge that there's some important differences in gravity from corresponding QCD computations. Among other things, the fact that we are all the time focused on, at least to this order, classical physics. And in gravity, a lot of new insights have been necessarily developed alongside with these brute force computations. So it's hard to develop the efficient technology from the start, but often with some brute force computations that then is analyzed, it's possible to develop some technology that provide more efficient constructions of computations. So we have today quite efficient frameworks for computation, but there's still a lot more to learn. For sort of a more general use, it's an interesting question to work on some automatization. Some of these things are quite automatic and could be used in programs that use these concepts. But we are quite far from that still, because as it has been so far, whenever we work out a loop order, we also have some new problems to consider. So it is still very much, to some extent, work in progress. And one of the current bottlenecks, if you're interested in getting involved, is actually related to the integral system. So the fact that we convert these computations to high loop computations, it gives us a challenge in identifying the correct integral by parts relations, solving the differential equations, integrals, and managing high multiplicities of these intermediate graviton legs. So we can do much more than higher loop orders than corresponding QCD loop orders, because we have the classical limit and some simplifications of what we're considering. But now we are getting to 4 and 5 loops, and it is challenging to provide these things. So a better analysis of what is the minimal computational needs would lead to a simplified analysis. But it's very reassuring to see that Amplitude tools are very useful. We are basically using all the tools we know of from the Amplitude field. We have the double copy, the KLT relations, we use unitarity. In some instances, we use spinor helicity. We have shifted towards a more covariant formalism. But we also use quite advanced things like this string-based CHY formalism, and also in some cases low energy limit considerations of string theory to help aid these integral constructions. And from corresponding computations in QCD and precision computations at the Large Hadron Collider, identifying IPP relations, solving differential equations, and recycling tools, programs, numerical programs has been very useful for the gravity ventures. So in conclusion, there's a number of tasks ahead. There's more data coming. There's future experiment. There's more precision. We know that black holes are most likely all having a spin. So having spin effects in play is a hot topic, and there's a number of recent papers. It's an interesting question to really solve this problem of deriving classical spin from amplitudes and using it in computation, verifying spinning Kerr-Hole considerations. There's also interesting questions related to radiation, validity of the exponentiation formulas or enhancing them to take into account new aspects. And currently at 3 loop, we have an interesting fundamental question about what happens at very high energy. This is currently an open question. Personally, I think quantum physics also has some right here. I mean, it's not relevant for the current observation, but there's some interesting fundamental questions related to how to embed quantum effects in all this. And definitely, if we are considering gravity as an effective field theory, higher order curvature terms are important to at least search for in the data. It's of course very small effect, but it is in principle something that could be interesting to find at some point in the data. It would really tell us that we have to deviate, at least from Einstein's theory, to some extent. Personally, I found that having an insight in string theory and amplitudes is useful. And there's some things we can learn about organization of amplitudes from geometry and string theory, things like twistor considerations that are helpful. So clearly there's more physics to learn, lots of topics for young people to get into and be interested in. And thank you for the attention.
Okay. Thank you very much, Dr. Bjerrum-Bohr. So we'll have time for a few questions now. So we'll open the floor for discussions.
Yeah.
So you can just raise your hands and ask a question. Yeah, so questions? Any questions?
So I can ask a quick question. So at some point you show some soft expansion. What do you mean by that actually?
Yeah, I didn't get the first part.
At some point you saying something about soft expansion in the one of your slides.
Yeah.
Actually, can you elaborate on that?
Okay. So this is back where we talked about the velocity cuts here. Yeah. So what happens is that when we are computing the classical effects, it's basically writing out an expansion in the transfer momentum Q. That means that what we are really considering is quite soft gravitons in the cut. So it's a value in order to derive the classical pieces in the cut, we have to do an expansion around Q equal 0 in the integrand. So by organizing the trees according to these velocity cuts, it allows us to easier extract what is the corresponding contributions that we have to consider. So we can do that by rewriting Feynman propagators into combinations of these delta functions and pieces where we still have propagators, but where the Q expansion is very simple. So an example of this is at 4 point we get something that is in some sense factorized in 2 3-point trees, plus something that gives us a soft residue corresponding to the Q small expansion. And then when we write down the integrand pieces, we can see that if we, for instance, look at a probe topology, on one side, we just have to include that piece where we have pulled out all the delta functions. And on the other side, we have all the delta function insertions at the velocity cuts. And this continues as we go up in order of next to probe, for instance, where we have one velocity cut on the right hand side, and we have all the velocity cuts on the left hand side. So we can organize what we put into the core. So these diagrams we can see as integrand pieces. And for instance, this blob here with the 2 minuses, it is simplified compared to putting in the full tree, because it's only the piece, here to the right hand side. So it's simpler than the full thing. So we can simplify what we put into the integrand before we construct the integrand, and thereby save computational steps. That is my point. But it also opens up this simpler way of thinking about higher loop integrands, because now we can organize according to this principle and thereby simplify the number of contractions and stuff we have to do in order to determine the integrand.
I see.
Yeah.
Also, one more thing. So you are saying that string amplitude may give a important insight. In the string amplitude, you don't have any S channel and T channel factorization usually. I mean, you have to take certain limit of that to have make sense of S or T channel. So
So for the spin amplitude, I mean, the expectation is as follows: that to leading order, it will of course give you the same as the spinless case, but the spin adds some additional factors to the amplitude that is then has to be taken into account both at the integrand level, but also at the integral level. So likely you will get some additional integrals with new coefficients, and those coefficients will evaluate to pieces that accounts for spin behavior. But the fundamental problem with spin is that quantum physics don't really allow that we construct large spin amplitudes. So fundamental spin is spin 2. So in order to derive classical large spin, one has to start with quantum spinning amplitudes, but take specific classical limits to get nice expression. So there's work going on at the moment trying to derive these classical contribution to spinning amplitudes, and there's some advantages in doing this from QFT and doing it from a bottom-up approach, because the amplitude methods allow certain simplifications to this that are helpful in these computations. But it is very much work in progress, and even the simplest cases of say 1 and 2 loop are still not to all orders in spin, and many of them are quite brute force computations as we speak.
Okay, so I think if there are no more questions, then let's thank Dr. Bjerrum-Bohr once more for a very interesting talk. Thank you so much. And